So we've learned that the gas law, the ideal gas law, is PV equals nRT. All right. Now we're going to look at a few different things that we can do using the gas law. First, let's define some standard conditions. Okay. We call the standard temperature and pressure. Okay. Temperature and pressure, and we abbreviate this STP. Okay, so STP conditions, when we refer to STP, or if it's at STP, we're talking about at this standard temperature and pressure. And the standard temperature is 0 degrees C, and the standard pressure is 1 atmosphere. So pretty easy to remember, 0 and 1, 0 C and 1 atmosphere. Okay, so at standard temperature and pressure, let's find out what is the volume, okay, of 1 mole of gas. Okay. Now we can substitute our values in there. First of all, we want to find the volume, so we can just solve this for volume, and that would be nRT over P. Okay, just dividing by pressure, and then we can plug in our values and see what we end up with. Okay. N is the number of moles, and we're talking about 1 mole of gas, so that would just be 1 mole. R is our ideal gas constant, which has a value of 0.0821 liter times atmospheres divided by moles times Kelvin. Okay, several different units in there. Arranged so that they will cancel with all of the others. Okay. Then we have the temperature, 0 Celsius, but remember we have to have it in Kelvin. Everything we do with the gas laws has Kelvin temperature units, or absolute temperature. So to convert this to Kelvin, we add 273.15, so that's going to be 273.15. I'll go ahead and put that in there, even though we don't really need that many significant figures. All right. And that's our temperature. We divide this by the pressure, which is 1 atmosphere. All right. So we see units-wise, we have atmospheres on top, atmospheres on bottom, Kelvin on top, Kelvin on the bottom there, and then moles on the top and the bottom. So we end up with liters. Right? So all this gives us, we have 0.0821 times 273.15. Okay, 273.15, and we end up with 22.43, or to 3 significant figures, 22.4 liters. Okay. Now we didn't even specify what gas we're talking about. Right. So any gas, it doesn't really matter what gas it is: helium, hydrogen, neon, air, any kind of a gas. At standard temperature and pressure, so at 0 degrees C and 1 atmosphere. So basically the air in your freezer, 1 mole of the air in your freezer would account for a volume of 22.4 liters, assuming your freezer is at 0 degrees C. Okay, so that's just It not something you have to remember necessarily, but it is a useful bit of information. 1 mole of any gas at standard temperature and pressure occupies 22.4 liters of volume. Okay. Another thing that we can do with the ideal gas equation is to manipulate this to find other properties of the gas. For example, we can determine the density. All right. Now, how would we get density out of what we're given here? All right. Well, if we look at density, how do we calculate density? Well, density is the mass over the volume. Okay, so here's volume. Do we have mass anywhere? Well, mass, we don't have mass directly, but we have moles, right? And so how can I express mass in terms of moles? Okay, so in other words, if I'm given a certain number of moles, n moles, let's say, and I want to convert that to mass, what would I have to do? Take my moles and I divide by the molar mass, right? So the molar mass, that would be grams per mole, and I'm sorry, I did this backwards. I'm going to multiply by the molar mass. Okay, grams to 1 mole. Okay, and I need to multiply so that my moles would cancel. So the moles times the molar mass will give me the mass in grams. Okay, so mass is the moles times the molar mass. I'll call the molar mass. So that means in my equation here, I can substitute this for N, which would be mass divided by the molar mass. Okay. And N would be the mass divided by the molar mass. That gives me the number of moles. So I can put that in here and rewrite my ideal gas equation to look like this. The mass times R times the temperature divided by the molar mass. Okay, just putting in this in place of N. Okay, so there's my substitution, keeping in the R and the T. All right, so now I can do a couple of things with this. All right. First of all, I originally wanted to get density out of this. Okay, so density is mass over volume. So let me rearrange this for mass over volume, and if I multiply both sides by the molar mass, I'll have the molar mass times the pressure, and then equals the mass. And if I divide both sides by RT, okay, and then divide both sides by volume, I'll end up with this. Okay, so the density, mass over volume, is equal to the molar mass times the pressure over R times T. Okay, now if that was too much to do in one step, let me just multiply this out so you can see it clearly. All right, so this will cancel there, and that's where I get the mm over here on top. And then I have this RT there on the top, so I can divide both sides by RT. And now those will cancel. And now I have volume over here. I want to divide both sides by the volume, and that will cancel there. And so that's where I get this molar mass times the pressure divided by RT equals mass divided by volume, or density. Okay, so if I take the molar mass of a gas times its pressure divided by RT, I can find out what its density is. Okay. Another thing that I can do with this is determine the molar mass of a gas. Okay, so I could say the molar mass of a gas is equal to the mass over volume times RT divided by P. Okay, so mass times RT, to move that back up to the top, kind of what I had originally here, and then divided by pressure and that volume. Okay, so molar mass will be the mass of the gas times R times the temperature of the gas divided by the pressure times the volume. Okay, so these are a couple of equations that may prove to be useful. Let me go ahead and rewrite that one there. The density is the molar mass times pressure divided by R times temperature. Okay, so these two equations will be useful to you. You notice we use a lot of algebra in this section on gas laws, a lot of manipulation of this equation and other similar equations, but nothing really fancy, just a little bit of substitution, given that density is mass divided by volume, and the molar mass also, substituting that in and finding our moles. Okay, so just with a little bit of manipulation, we can come up with these two different equations to give us different information about the gas, the molar mass of the gas, if we didn't know it, or if we knew the molar mass, we could find its density. Okay, in either case, not necessarily knowing the identity of the gas. All right, so these may prove to be useful to you in working some problems.